Good afternoon, everyone. We are going to present or talk about the paper.
You should introduce yourself.
Okay, I'm Hriday.
I'm Pedro.
Yeah, hello. And we're going to talk about the paper Multi-Head Transformers Provable Learn Symbolic Multi-Step Reasoning via Gradient Descent. The title is a mouthful, and Pedro will probably explain a bit more. So this paper is a theoretical paper. It is built on the experiments conducted by another paper, which empirically proved a few things. We won't really go into this paper in any detail because we want to give time to our own paper, but just in a hand-wavy way, this paper went from shifting focus over reasoning over natural language to some symbolic tasks. So some abstract symbolic reasoning. So they had two tasks, which was once they're given a tree, you want to find the goal to the root, the path from the goal to the root, and another task is finding the path from the root to the goal. So before we explain anything, a question to the audience: what do you think is the more difficult task? Going from the goal to the root or root to the goal? So if we have a prompt which we are given the edges of the tree, and we have the goal, which is a leaf node, and the root. So what is the more difficult thing? So is going from the goal to the root more difficult, or from the root to the goal?
Goal to the roots is easier.
Yes, yeah. And could you explain why? I mean, we'll do it as well, but why do you think that is the case?
I think from the roots you should figure out which nodes should be carried.
Yeah. So this paper did not prove why this is the case, and as Alireza mentioned, that is the actual idea. This was actually proved in another paper which talked about like how difficult this task is for choosing the correct node, and we will talk a bit about it as well. But coming back to this paper, so they experimentally reduced some algorithm from going to the root to the goal. So yeah, finding from goal to the root was easier. So what they did was, to go from the root to the goal, they first found the path from the goal to the root and just reversed it. So does that make sense? Okay. So that is what they found experimentally what LLMs do, and they had some proposed mechanism of how this works. So they have this deduction head kind of a concept where these are the list of edges. So the parent to the child, and you have a goal. So what you can do is find the corresponding B that matches G, and just get the A and B with it, and your current will shift to A. So it's basically just recursively finding the parent, and you'll find the B which corresponds to some A and find its parent and find the path like that. So yeah, this is what they did, like search for edge in context, where current position is the child node B, find corresponding source node and copy source to the current position. And again, in a more hand-wavy way, they implemented the transformers with some L layers, and they said that each layer will correspond to finding a hop. And the reason why I mentioned this is we are not going to go in this detail at all, but our paper does it in a very different way. So this is probably some background into what is actually happening. So yeah, any questions so far?
Can you explain the algorithm one more time? I don't understand.
Okay, so you have the goal, right?
Yeah.
So it's finding, say, 9 or something. Then you find the corresponding child that corresponds to 9. So, for example, if 9 had like...
Oh, I see now.
It's the parent, not the child.
Yeah.
It's like it depends on what you call a child or parent. Isn't that a parent? Like
Yeah.
normally you go down and you find the child, and
Yeah,
when
kind
you go
of,
up,
yes.
you find the parent.
Yeah.
Okay.
So, yeah, any other questions? Okay, so now we'll go a bit over, we'll just digress for a minute, and we'll talk about another problem which talks about why this forward reasoning or forward path finding is a bit of a difficult problem. So for that,
What does the symbolic thing mean?
Just reasoning over another structure, not just natural language, like anything with symbolic. So it can be a graph or a tree or anything. So what? Okay, so this example is they give a star graph kind of a thing, which is
a tree.
yeah. So I think I can probably introduce some notation as well. So this is a graph. D vertices. With d parts of length L from the starting node, and you just have the edge list. And you have, say, this is N1, this is NL, and you have this path to find, and it should output like, so this is N2, this is N3, so it should output N1, N2, N3 till NL. So this is what the task is, and as simple as it looks, it is actually a very non-trivial task. And what is the main problem is, so this is a forward approach. So you're finding, you need to go forward. So you're finding the path from the root to the goal. So basically, it's like, this paper also uses another paper's result. So it's said that due to certain styles of training, so we'll probably talk about it a bit later, but there's this thing where you're using teacher forcing. It's like a supervised autoregressive training method. So most of the methods that use this teacher forcing learn to cheat. So what they do is, they just try to find some kind of like a mechanism where when you're given such an edge list, you're just, if you are at this node, you just need to find the node that corresponds to the next list in the adjacency matrix. So that is in a very hand-wavy way what this mechanism is. However, when you are starting over here, it will not hold because you have around, for example, D options to go to. So during the testing part, what they do is, in reality, they just take a random walk. So the testing accuracy is limited by 1 by D because they do not have supervision on what to do next. So yeah, that is what the paper did. And what it talks about is that once this cheating strategy is learned, it is very difficult to correct itself. So it has a bit of a proof, which we can go over very quickly.
Can I just clarify the problem? You're given like the set of edges,
Mm-hmm.
and then you're given 2 points, and you need to output a path from one point to the next.
Mm-hmm.
Or-
Yeah. Okay. Okay. So the proof is okay. So I think I can first tell like what this statement is, what this talk about. So the thing is that once this flawed cheat strategy is perfected, learning the correct path is at least as difficult as learning full parity functions. So I think Chaba and a few other presentations did talk about that. So we will show how this happens. So okay, consider 2n plus 1 vertices, and just for the sake of simplicity, let the vertices be ordered like this. Okay, and my goal here is to get to positive n. So consider these as my nodes itself. So how I'm making this problem is, I have my first, like the 0th node over here, and I connect to 1, and minus 1. So now the rule is that you have a binary string and for you follow this, that if x of I equals 0, what you do is you go from I to I plus 1 and you go from I to minus I minus 1. If x of I is 1, you go from I to minus I minus 1 and minus I to I plus 1. So you're just kind of switching. So for example, if the string was like 0, 1, 1, 0 or something. So you go from this and then you switch and then you switch back and you keep. So now, if I say that I have to reach the positive index n, if I start at 1, that means that I need to have an even number of flips to reach n. Is that understood?
Wait, can you explain what happened from the, like there was, you started 0 and then why did it split apart?
Yeah, this is just the formulation.
So yeah, we are trying like to, that problem from the star graph, that tree, we're trying to represent the problem of parity, of trying to find the parity through this problem. So we are just basically like, take for example the upper path. So we start at 1 and we are going to go up and flip the sign like every time we reach a number 1. So yeah, I think it will be a minus, no?
That's fine.
Yeah. So the idea is that like we're flipping this sign every time we reach a 1, so that we can represent the parity problem as a star graph problem.
Right, so when you say flip the sign every time, so that means that the 1, 2, 3, 4 are representing the bits of the input, with a positive representing a 0 and a negative representing a 1?
No, these are just the
No.
nodes. These
Yeah.
2n plus 1 vertices.
Yeah, but why is there like a 1, 2, minus 3, 4,
Yeah.
5?
Okay. It's because like every time we reach a 1 in the sequence, we flip the sign. So
Yeah.
we go 1, 2, we reach the first one, we flip it from plus to minus, and then we reach the next one and we flip from
We flip
minus
it
to
to
plus.
minus. Yeah.
Okay.
So it's just like a, yeah.
So maybe is the thing you're trying to say like there exists a reasoning problem which
Mhm.
is this graph
Mm-hmm.
where we don't know what's the right path, and
Yes.
the right path is generated by this x which is drawn from some binary distribution and is unknown to the learner,
Mm-hmm.
and then based on that thing we construct this graph, or the reasoning problem is constructed
Mhm.
like that,
Yes.
and then we have to learn this basically parity to understand where
Yes.
that's what you're trying to say.
So yes. So
And
it's
the input to the transformer will be the edges of this graph.
Yes.
And you're saying that is basically going to encode the bits of
Yes.
that you want to find the parity
Yeah.
for.
Yes. And like the
Yeah.
point here is like, this is the parity problem, and if you thought that the parity problem is hard enough, we have the star graph problem, because like the parity problem just have 2 branches here. The star graph problem have D branches, so it's at least as hard as the parity problem.
yeah. So the main idea is that finding the correct path. So choosing between 1 and minus 1 is like the parity problem itself.
Wait, I have a question. Are they just trying to show that this problem of this graph star thing is
Mhm.
as hard as parity?
Yes.
Isn't that like, so graph, I think this problem you mentioned is called graph reachability, and it's like a complete problem for log space. And parity is known to be in log space. So I don't know, like in complexity theory, it's well known that graph
Okay.
reachability is much harder than parity. I don't know if that's,
So what they say is that, like once this trick is learned of the cheating thing, it's called the clever Hans cheating trick. So once this cheating trick is learned, to recover back is as difficult as the learning the parity. That is what they state.
But I think here we are making a very special graph which is equivalent to the parity problem, right?
Yes. So
But
this
in
just
general,
to-
the graph can be
No,
much
but
harder.
I
I
mean, it's
guess.
the same like what Lad said, that if you were to say that graph reachability is harder than parity, that means there would be a reduction from graph reachability to parity,
Mhm.
which is what this is, right? So,
Mhm.
so maybe this is a known result, and that's what Lad is talking about.
Okay.
Right. But it's still good to know, good for us to.
Okay,
see
okay.
the result, right?
So yeah, this is some intuition on like choosing the correct path when going forward is difficult. So we showed all of this just to show that.
So what? Can I ask a question?
Yes.
What is the hard parity problem that we're talking about? Can you just clarify for the sake of everyone in the class?
Mm-hmm. So it's like finding the sum modulo 2 if it is odd or even given a binary string. So
I mean-
you're finding the even number of ones.
That's not a hard computational problem, is it?
It takes linear in the number of bits. You can just compute the parity for 2 bits at a time, and then you're done.
Yeah, but for transformers, it is difficult.
Yeah. So
Is it difficult for transformers? I mean, I can find the ways for a transformer to do this very easily. I think that the problem maybe you're talking about is learning the parity is hard. And that's what we were talking about. When you have random instances and the neural network needs to learn to compute parity, then if
Yes.
you're using gradient methods, then the gradient methods are going to take exponential number of steps in the lengths of the parity problem to learn the correct function, the correct execution of the parity. This is the hard problem that we try to reduce another problem, which is to train a transformer to solve this problem where you are given instances, inputs of graphs, and the graphs take this very special form, trees or whatnot. They have 2 arms. And then the argument is going to be the learning of these graphs is at least as hard as the learning of the parities.
Yes.
Because
Right. Yes.
it's kind of like a weird argument though.
Okay.
Because when we were arguing that learning parity is hard, we were arguing that it's hard for gradient descent. So it's not unconditionally hard, it's not hard for everything, like there are algorithms that are efficiently learning
Yes.
it. And now we are still using gradient descent, but it's for slightly different data, and then okay, so this kind of semi-convincing, this argument, I would say. Like I wouldn't accept it as a proof of hardness,
Okay.
but it's true that this is what the paper presents, and so you're just presenting what the paper does. But to show that the transformer will not learn it, I think that one would need to do more things. But it's a good proof idea.
Okay. Yes.
Yeah,
Yeah, on the paper
it's kind of
they-
like indicates that it's probably hard.
Yeah,
Yes.
the paper they just do this reasoning. They don't go deep in the math. They just say
Yeah.
that like, okay, we're training a transformer with gradient descent in an autoregressive manner, and like you have very many pairs like here where you just have to find the next node, the next node following an edge, because those here are like a directional graph. And like the transformers in the end, it will be biased in just following the next and just outputting the next one. So at the end, it will like the loss will be heavily biased toward this behavior, but the behavior of like learning the first one will be like penalized, and after the transformer learns to do this forward thing, it will not learn to to learn the first one, because it has to plan, it has to go backwards and then forwards.
I guess maybe at that point you could say that then the problem really became equivalent to learning a parity function. So if you told a neural network that in this graph you have to figure out which node comes after 0 in the output, in the path to the goal, then that's equivalent to telling the parity of
This string.
of the corresponding bit string that was used to generate the graph.
Yes.
And so if it was possible that gradient descent can solve that, then somehow gradient descent sort of feels like it would solve the parity problem as well. Yeah.
I have another question. The data, is it of the form that each problem is a different like set of edges and a different point to other point? Is it like in context it needs to solve different problems? Is this what it's learning, or is it like you have a fixed graph and then you get a bunch of examples and then you learn?
No, they use various different graphs. So, for example, for the parity problem, you can basically have 2 to the n many graphs to train your transformer, and the amount of bits you are using. So yeah, they train with lots and lots of different graphs.
Oh, okay, so the actual prompt is like this whole graph information and then 2 points. So in context needs to learn the map.
And the 2 points are always going to be 0 and 5 or something, right?
So this is not really our example for our paper. This was just to show that deciding what step to take from the vertex is as hard as learning the parity problem. So don't remember, like this is not what we are. Our paper is based on.
It's not the main thing.
This was just a reason why, like, the forward look ahead thing is difficult. That was just the motivation to give like some theoretical motivation behind that.
Yeah. Before going, are you finished with this?
Yeah.
Okay. So like before going on the notation, I just wanted to show. Maybe it's not entirely clear, but imagine, for example, we have again one graph of this form here, and we have the tasks like for forward and backwards, and like we have the root here, and we have a goal here, and okay, we have arrows here, okay, and for the backward, it's a lot easier for the transformer will receive as an input all the edges described as the relationship between 2 nodes, and which one is the goal and which one is the root. And like for the transformer, it won't be like easy as it is for us just by looking, because we have like, I don't know, spatial reasoning. We can just look at this graph, and forward and backward is easier for us. You can just imagine that, I don't know, the transformer look at it like as a scrambled graph. So it isn't straightforward to know which path you should take when you're going forward, because going forward you have to make choices, and going backwards you do not have to make choices. Like each node here just have one parent, so you basically follow a straight chain, and that's it, the problem solved. So now basically saying this but more formally, we have, okay, the definitions here are important for the theorems, because the theorem is the theorems and the results are stated in the form of this notation here. So just first of all, I'd like to define what a tree is in this context. And okay, we have a tree. We use this fancy T here to represent the tree, and it's a set of 3 sets. So this is the tree. Those here, this is one. It's a set with all the nodes in the tree. So for example, for this tree here, the nodes would be 4, 2, 3, 5, 6, 5. Yeah, all these numbers here. And then we have the edge set, which is the relationship between the nodes. So it's basically these arrows here. And we have the goal node, which, as indicated here, it's, in this case, node 8. So yeah, we can define the edge set as being
Uh-huh.
Oh, I think we need to close the
Syntax error.
Syntax.
Okay. Yeah.
I thought they were more transparent.
for NDI. The edges, the node set. So in here we have our root, the definition of our root, and the formal definition of our edges is this. We have this function p, which denotes the parent of a node. So we have a pair, the parent of node I and the node I itself, and all the nodes we're considering here to have this kind of edge is all the nodes in the edge set except the root node. So we wouldn't include, for example, the root because it doesn't have a parent. The function p doesn't work with the root node. So next we have what we mean by pathfinding. And of course, we have two types of pathfinding. One from going from the root to the goal, and one from the goal to the root. Okay.
One, can you have multiple parents coming from the same node?
No. Each node has only one parent. Otherwise, it wouldn't be a tree.
Yeah.
So
You can have multiple children, but
Yeah.
just
Yeah,
one.
and
that-
if it had like multiple parents, it wouldn't be, any of those results would be valid.
Okay, good.
Yeah.
And then, but that's defined in this edge definition somehow?
Yeah, because P of I is a function,
Yeah.
right?
Oh, right.
So everything only has one parent.
Yeah. So
Okay.
the first one we have the P, G to R, which is go to roots of a tree. It's defined as a sequence of the goal, then of the goal. And then, of course, we're going to read the root. And basically, as you can possibly guess, the root to goal is basically the same thing, but reversed. So we have root, and then we have the sequence until we get to the parent of the goal, and then the goal itself. So any problem until here with these definitions? Okay. So yeah, this is the one we're calling backward. and this is the one we're calling forward. And now let's go to the input embedding. Um, So for each one of our edges, we'll have one embedding for that, and those embeddings are of the following shape. So, okay, we first first of all, we are going to have an embedding for each one of the tokens, which means each one of the nodes, we're going to have an embedding for that. And this is what this A here stands for. It's the embedding of one single node. So you can take each node from here, from V, and this will be the embedding here. This is how its embedding is represented. And then we have the embedding of an edge, which is basically we're taking the embedding of a node and its parent. So the embedding dimension of a node is just D1. And so the embedded dimension of an edge, it's 2D1. We're basically concatenating the embeddings of two nodes to get the embedding of one edge.
Mhm.
And okay. Now we have the definition of the transformer we are using here, and okay, let's add. And we have a couple more definitions coming out. So this is like the usual transformer we are already used to, but with a couple of parallel heads. So let me explain this expression here. So we basically have the operation for the transformer. Here we have the paper says multi-head transformer. So this is the equation of just one head. It has an input as the embedding, and we did do the transformation with the key with the key, query, and value matrices applying a softmax, and we just basically concatenate everything, and we have an output matrix here that will calculate our output. And just a little bit of notation here, we have this big H, it's the amount of heads we have. And yeah, so the title of the paper, when they are talking about multi-head transformer, here we are going to use just 2 heads. Like they're showing that, okay, we can do it with just 2 heads, so probably we can do it with more heads, but we need just 2. We can't do it with just 1 head, but from 2 on we can. And instead of papers like that one that they talked about, that Brickman paper, they use multi-layers with just 1 head, but here they use multiple heads, and it showed that instead of not learning the task, it is able to learn it. So the test they talk about is the symbolic multi-step reasoning, and what they mean by that, it's basically this, solving this tree. And specifically, the forward thing, where you want to find the path from the root to the goal. So the algorithm you have to use for that is that we have to start at the goal, go up each one of the nodes until we find the root, and keep track of, while we go up, we have to keep track of each node we visited, and then we have to output it in the reverse order, so that our output have the right order to go from each one of the nodes. And yep, what they do here, it's through 60 pages of proof, mathematical proofs, to show that just by using gradient descent in this transformer architecture here, they can provably learn it. The transformers can provably learn it. Yeah.
Pedro, questions?
Okay.
Right, yeah, so how many heads and how many layers do they need? Like, does it scale?
It's just 1 layer.
Just
One
one layer.
layer.
So for the forward task, you need 2 heads,
Uh-huh.
which I think we can talk later with the intuition. But for the backward task, you only need 1 head.
Yeah.
So
Oh,
1
okay.
layer, 1 head for the backward, 1 layer, 2 heads for the forward.
Okay,
Yeah.
so it doesn't scale with the size of the graph or anything?
No.
No, it's just a simple algorithm with just a couple of weights. We are able to learn everything we need for this problem, and they show that also it's possible to generalize with trees of other size. So if, for example, you learn from a tree of depth 3, for example, you can generalize for 3 of depth 4 as it's here, or even longer depths. So
what was again the data that we are learning this from?
So, okay, I'm getting there. It's the next step.
Okay.
Wait, what was the question?
What is it?
What's the data we're learning from?
Oh, well, before that, can I just clarify, the previous paper you
Okay.
said they had 1 layer, oh, sorry, they had
No.
multiple layers, 1
Yes.
head?
No, they had multiple heads as well.
They had, oh, I thought you said the previous layer was saying they couldn't learn or something, with multiple layers, 1 head or something, no?
No, they could learn.
Oh,
So,
what was the relation to the previous paper, cause you had brought it up, I think.
so the previous paper had L layers
Yeah.
and multiple heads. Like this paper has 1 layer and 1 head for backward, 2 heads for forward.
Okay. Yeah.
So basically they wanted to prove that you don't really need a deeper architecture.
I
You can
see.
probably just increase the number of reasoning steps to get the output.
So how does that square with the hardness of this? Like you were saying, this is as hard as parity, which is
Yeah.
hard to learn with gradient descent. So how is it that this one can learn?
Okay,
Data
so
will be different.
Okay.
Like even this paper, to go forward, it first learns the backward path and then reverses it.
Right.
So it is just to understand why just the forward only approach is difficult.
And the fact that you can do reverse without
Yes.
chain of thought or
Yes.
anything. Right.
Yeah, so that is the thing. There was someone
Wait,
else.
what was
Yeah.
the last one, you can do reverse without chain of thought?
Is this with chain of thought or like your zero shot? Trying to.
No, it's like chain of thought, yeah, multi-step reasoning.
Okay, this is okay.
Yeah. So, okay, we'll get any more questions before we continue? Because I think a lot of the things that were asked will be covered in the next step, like the data set and the reasoning steps. Okay, so let's go to here. And can everyone see this, or is it too small? Okay, no? Okay, I'll try.
I have just a high, like, in terms of this architecture, are you gonna go into any more detail about the precision of things and the, like, layer norms and stuff like this? Or no? Like, cause all these things seem to matter a lot, and I'm just wondering if they talked about it.
Okay, no, they don't talk about like layer norm, but we have the exact update equation that they use, and it's basically the simple update we're used to. They do not include like layer norm or anything.
And they have attention and multi-layer perceptron. Or is this just attention? They just have attention layers, or is there MLP layers?
No, it's just this.
It's just
this is everything. Like,
Attention, yeah.
yeah,
So they just have attention,
Yeah.
and then they have a few of them,
yeah,
2 layers or something.
Mm-hmm.
yeah. So in
Okay.
here, like, oh, they just have one layer.
Yeah, one layer.
They have 2 heads
Heads.
in like the
Oh.
training experiments they do. They have there's 2 heads and 1 layer. It's basically this equation. The E, it's
Yeah.
our output input embedding,
Yeah.
and we have this matrix here for the key and the query and the value, and it's basically that we get a head, we calculate the output of a head, the output vector of one head, we concatenate it with other heads, and we apply our output matrix, and that's all they do.
Mm-hmm.
There isn't any other fancy trick, and the gradient descent is the simple gradient descent with the laws. Yeah, just that.
Okay.
So okay, I was just talking about the embedding here, the input. So we have here this type of input. So we are defining as X and Y inside the embedding matrix. So the embedding matrix is basically the graph as a matrix. So we have like on the first lines, we have a couple of all the edges. So you can see here, for example, the connection from 1 to 8. We have here 1 to 8. From 2 to 1, we can find it here, 2 to 1. So this is basically the graph, all the edges of the graph represented here in a matrix from parent to child. And then we have as kind of a special 2 final columns. It's the root and the goal. You can see here that the root doesn't have a parent because, yeah, we just put 0. They just use 0 to represent that the root, which column is the root. So it's always the last to the previous to the last, and the goal is the same thing. The goal doesn't have a child, like it's our goal, it's the end of the graph. We don't care about anything that comes after it. So it's basically that, the representation. So this is what goes inside the transformer, and then when it goes outputting the values, we have this. So
Wait, sorry, I just have a question. How does that, that's just one giant, it's not one token, right?
yeah, yeah. This is the embedding matrix. So here we have the embedding of just one node, and here we have the embedding of one edge, which is basically the embedding of 2 nodes concatenated.
Yeah.
And here we have the embedding matrix, the embedding of the input. So here we have multiple of those concatenated. We have exactly the embedding of all the edges in the graph, plus the root and the goal. So this isn't like the embedding of just one thing. It's the embedding of all the inputs, all the edges, all the goal and the root.
I think it's a bit more clear over here where they set up the embeddings for that task. So I think this is the same thing as they do over there. So it's just taking all the edges and stacking them together.
Yeah.
Yeah, so it's just a part of
Usually
this.
the input's like one long sequence of some amount of tokens,
Mhm.
each of which are of the embedding dimension D.
Mm-hmm.
And I'm just trying to understand how many tokens there are.
So it's like the number of edges, L of t,
Yeah.
and plus 2 for your.
Yeah.
So this is like till the number of edges, and you're
Okay.
just adding these two columns.
I
So
see it. And
this
then you
is-
stack the two tokens that are together as one vector of 2D1 dimension. So
Yes.
each edge is represented is one token.
Yes.
Or you can think of it as 2D dimensional
Yeah, well,
tokens.
that's fine.
Yeah.
In like this example here, D1 is just 1, so you don't have to worry too much about the size of the embedding. Just like D1, it's
Oh. Okay.
just one.
I mean, they just do it for the ease of explanation, but formally, yeah, it's D1
You
dimension.
can have any
Okay.
size you want.
Yeah.
Just one more thing here. Okay, so we have the definition of our problem, the transformer, and now how the transformer generates its output. It's based on autoregressive manner. So we have here the output. We are calling it O hat because like the output and an approximation. And at output token k plus 1 will be, it will take the 3 and the parameters of the transformer, and we're just going to use f, which is our transformer function, with e, k, okay. So that's it. So EK, it's the embedding matrix like this. And at each step, we're going to generate an output, and we're going to append to the end of E, of the matrix E. So it's basically our input is growing with the outputs. We're adding the outputs to the input, and we are applying this function, the same function, over and over again without changing anything else. And it's basically that. That's the mechanism that this transformer operates to generate the output. So,
Wait, so is e to the k equal to O hat k plus 1? Is O hat k plus 1 of length k plus 1? Or is it a single token?
it's a single token.
Okay, and then it gets appended to e to the e.
Mhm.
Yeah, it's here, it's upsized.
I see. So I guess this f e whatever thing takes like the last index or something.
Yeah, the last column.
Yeah. Yeah, the output is just, yeah, exactly. We have here,
Like minus 1. Yeah.
do it like this. So, yeah,
Okay.
this here will be just, the output will be just one column here with a parent and a child.
Mhm.
So, do you want to go over the backward reasoning, or do you think it's best for me to?
So is it like, for example, from 8, 8 was our previous goal, and then we have found the parent of 8.
Mm-hmm.
Then 1 is gonna be the kind of the next goal that we should find,
Yeah.
and we apply the same function over and over.
Yeah.
We get to the
Yeah.
root.
Yeah.
Yes.
Nice.
So let me show this in this example here. We're exactly right. So for this backward task here, in these three, this example 3 here, we have this. This is how the problem is represented for the transformer, right? So we have the edges, the root, and the goal, and so the transformer at the start doesn't have any information about like where it's supposed to, where it's going. It's just have to start outputting the tokens. So for the backward task, we want to have this sequence of nodes outputted from the goal to the root. So the first one it's going to output, it's going to start at the goal, which is 8, And it identified here that we have one line, one column that's 1 and 8, and it's basically going to copy this one and put this at the output. And at the next step, we're going to take this output and put it on the input in an auto-regressive manner, and it will just keep going up. So it identifying this pair, 1, 8, and the next one is 2, 1, and the next one is 4, 2, and 2, 1, 4, 2. When it gets to 4, it will see here that the root, as represented without a parent, will be 0, 4. And when it gets to 0, 4, meaning that doesn't have a parent, it's over. It's basically this. So here, the root's found, problem solved. So this is the backward reasoning, and that's basically also why it's really important to learn to do the backward thing before doing the forward thing, because as you can see here, the forward path is basically here already, right? 4, 2, 1, 8. It's easy to see how you do it after doing it backwards. So for the transformer, it becomes very simple, and they have to extend this problem a little bit to fit the forward thing, for the reasoning, but I'll pass it for Hidre to explain a little bit more the formalization of this backward reasoning thing.
Yeah, thank you. So the backward reasoning, the setup is like this, where the input embedding is like stacking x and y. So as I explained, and you can see in the figure, is just like the embeddings of the edges, and then the last two is you have the root for the y, and since you don't have any parent, it's a of 0, which they define as the 0 vector, and the same, the goal doesn't have any child, so that is how they do. And this is the dimension, and the ground truth is like this. So you have the goal, like the embedding of the goal, then you have the parent and its parent until you reach the root, and this is of this dimension, like 2d1 into m of t, which is the length of the path, because number of steps you need to take, and they define the weights in such a way such that this, when you put all these things in this formula, you get this. So if you want, like, it's okay, will you agree? Like, it is true, yeah, okay, thank you. Okay, so what they do is they kind of slice what x and y is at the k-1 reasoning step, and okay, I think I can write the dimension actually. Yep. So yeah, they just slice x and y, and it's just 1 to d and d plus 1 to d, which is like this slice and this slice. I think it's already done over here, and you are left with this equation for the transformer, which is yeah, so this is the equation for the transformer. And now what I think we all saw is the main mechanism here is how can it find how does it find the parent in this entire edge list. So we can okay, I think I'm going to use this. Okay, so yeah, I'm sorry, I forgot. Like, by the way, this is the last column of x, which will, okay, which corresponds to, oh, not the entire thing, just the goal node. Is that fine? Okay, so over here, what they show.
And that's the only thing querying, yeah.
Sorry?
That's the only query node is the last token.
Yes.
And it checks all the other values, the keys.
Yeah. So for any. So they want to show that for any, like for alpha belonging to R, you have B, which is the trainable parameter, such that this holds. So what does this mean? I think they have an assumption over what A is, which I will write, is defined as for all the nodes, which will be D1, yes. Yeah. Okay, so if this holds, they state, or they want to say that as alpha tends to infinity, the ground truth for a tree correspond to yes. So this is what they show, that as alpha will correspond to infinity, the output of the tree will correspond to the true value. So why does this happen over here? So if I look at this equation over here, and if I just try to compare just from a broader perspective, so if these both correspond to the same token, this holds, and if I say alpha tends to infinity, so if I take a softmax over this quantity, it should give me like a one hot vector, or it should have like the probability mass should be concentrated at one single point. So yeah, it's like a one hot vector.
It's diagonalizing the matrix. The
Yes.
matrix.
Yeah. So is this fine? Like if as alpha tends to infinity, when I take the softmax, yeah, it diagonalizes, and it's like a one hot. Okay. Yeah, it's like a one hot vector kind of thing. So what happens here is if these two tokens are the same, it assigns the highest, like it assigns that value over here. So I think
What is A and what is S? What's S?
S is like the number of nodes in total. It's like the set of your nodes.
Okay, that makes sense.
Okay, so just to think in a way, okay, so this will be like D1 and 1 is the dimension. This is D1, D1, and this will be, okay, I think, yeah, there's a transpose, D1, L plus K plus 1. So, these are the dimensions. So just to infer what is happening over here, at the end this will be like a vector of dimension. Is this inferred? Is this fine?
That whole thing is of that dimension?
Sorry?
I mean, each output is not that dimension. Wait, what?
Each output?
Each O, little o of capital T?
Yeah, no. Only this.
Oh, that.
Only this quantity. Yeah. So
Yeah.
what this correspond to is the L plus K plus 1 is just the set of all the y's, like y1, y2. I mean, multiplied by something. So okay, I'm just writing just for the sake of it, explanation. like this. So what does this mean is, when you have this kind of a one-hot encoding, this will correspond to the point where the goal, like the child is the goal, and you are just finding the parent of the child. So it's just assigning the highest probability mass to the point where y is the goal.
Right, because B is like the inner product matrix
yeah.
that takes embedding of some node and embedding of another node, and it gives you 1 if they're
Yes.
the same node, and gives
Yes.
you 0 if they are different
Yeah,
nodes.
exactly. So that
Sorry.
is the
So isn't B the key and queries that we have learned for the transformer?
it's the
Okay. And what Roshan was saying just right now, it was
Mhm.
like when the goal and root is the same, or no?
sorry.
I mean,
No,
when does
no,
B
B is just going to work for any pair of nodes. It's
Mhm.
going to take 2 vectors corresponding to a pair of nodes,
Yeah.
and X transpose BY is going to be 1 if X and Y encode the same node, and 0 if they don't encode the same node.
why this B is what I'm looking for when I'm learning the transformer?
Because that's the
That's how
key
they
time
set
to
up the
query. Yeah.
weights.
Yeah, they take those two matrices here and transform, multiply them together and make this one. And they say, oh, let's impose that the weights are from in this shape right here. And this is good for the proof and for the for the following of the algorithm. So it's basically, it's good for the proof, it's good for understanding the algorithm. So they just impose that the K Q matrix have that shape and those values.
Sorry, I also I didn't get that subject to AT. I mean, what is the identity matrix over there? And
That's what I was saying.
Okay.
So if you take one row of A and a different row of A transpose and multiply that by B, that should either give you 0 or 1.
Or 1, yeah.
Oh,
That's
okay,
identity
got it,
matrix.
okay.
And it gives you a 1 if they're actually the same node, and it gives you a 0 if they're different nodes.
Okay, yeah.
So are we assuming we are going, the transformer converges to that B, or?
Yes.
Yeah.
So I mean convergence, and we'll probably get to it in a while.
Yeah. We won't be able to get to the proofs of the convergence, but the results will definitely show it.
Yeah. So this was just to explain how the mechanism of the backward pathfinding works. I think Pedro can go into the forward part. So it's just to give.
Oh.
I think you can erase this.
Okay.
So as you said, I mean, here we were only using one head for this thing. So the main part for the forward is that the one head will look at the pathfinding thing, and the second head will act as a switch between when to move backward and when to move forward.
I'm trying to. So
Yeah.
okay. So the forward thing here is really similar to what we did for the backward, but just with a switch. A little bit of a twist that, like Hidey said, we have to keep a token for task switching. So we're going to first do this forward task here, and then the backward task, and then after reaching the root node, we are going to identify like, okay, now we need to output the result that we are keeping track of. So we have like here. Now again, the embedding matrix. Here is the difference here. We have not just the X and Y, but we have also a Z, which is our token here. So, okay. And it's the X and Y, it's basically the same thing. But now we have this token here as F, and as we go into the embedding matrix, we'll get to the first. So we're basically keeping track of this token here. It will be, for example, the example I'll give right there, it keeps an F as the token, and after it reaches the goal, the transformer changes the output token here at the bottom to backwards, so that it can switch the task. So the ground truth here is a little bit different. I think this is one of the main things of the paper, because yeah. Okay, so the main thing here is that the output path, our ground truth, it goes from the goal, like here, it goes from the goal to go to the root.
So this thing that you're going to explain now is basically what do you need to do to implement reversing, and how to detect when you are, detect when you reach the root and then do the reversing.
Yeah, yeah.
So
And yeah, it's basically the same thing. We're going
Right.
to do the same definition here, and we're going to have assumptions about the weight matrix. A really nice way to put the zeros and the actual weights,
Right.
and that will get us to have a nice representation, easy to.
But I was wondering, because that's like a fairly standard problem, and we've kind of talked about these sorts of things when we're talking about RASP and stuff like that. Like maybe it's better to skip that and go into the other stuff which is specific to this problem. So for example, one open question was, how is this being trained? Like what data is being given, etc. Right?
Yeah, yeah.
So because just the reversing, I mean, I'm sure we could all construct
Yeah.
a thing that reverses stuff, right?
Yeah.
Yeah.
Like it's up to you, because we only have like 20 minutes. So
Okay, okay.
So it's
Yeah.
probably the
Yeah.
yeah, I mean
Yeah, like, okay, so the output graph here, let me just finish it. It's basically this. We have the goal, and that's it. We go from the goal to the root to the goal. So this is basically the data we are going to use to train the model. So you can see here the reasoning steps. The reasoning, they say that the multi-head transformer can learn. It's basically learning from a data set which contains the reasoning. So it's not like extrapolating the reasoning. It's basically taking that reasoning and putting inside the transformer. It isn't learning like a new strategy or something. We're basically imposing it to learn that strategy. And what they do with this token here at the bottom is, yeah. So okay, we have here the start of the same problem from the same tree, but now we want to not go backwards, we want to go forward. So what you have here, the embedding matrix, it's really similar to the last one. The difference is this bottom line here, which we are using that token I talked about, which is here like F and B. So you can see here at the end of the algorithm of the matrix, B is the token, so it will start to go backwards. So it output here like before. It will output the first edge and the next edge until it reaches the goal, which is the 4. And after that, it will output a token with F. And F means that it now reached the goal, the root, and you basically output the path that it went through, but in reverse. So it will output first 4, then 2, then 1. Oh, sorry. Yeah, 4, 1, 2, 1, 8. So we'll go 4, 2, 1, 8. This is the solution of the problem. And that's how this token here is used for that. And yeah. For the weight matrix is basically the same thing, but bigger, because now they will actually use the two heads. The first example we had just one, but now they will have two heads, and the weight matrix will be bigger, and they will do like impose a really big structure in this matrix here. But eventually the algorithm is able to learn that. And then we can get to like the last part of the paper, which talks about how it uses the gradient descent to learn it. So first of all, we have I'll write in the loss. Okay, I'll write the loss here.
Yeah.
Okay, so first of all, we will have here the train loss. So this is the loss here. Like I said, we are basically taking the reasoning, the data set already with the reasoning done, exactly that reasoning here, and we are going to apply it to our loss function. So we have here, that's the ground truth, that's what the model is outputting, and we're going to use it to learn how to solve the problem. And here we have multiple different graphs for this data set, because we are using ptrain, which they define as being a training distribution over all trees of at least depth of 3. So yeah.
Sorry, is it not learning each token independent? Because like you have this like Frobenius norm, which I guess is over all sequences that it outputs of this length. So it's not learning each token one by one, but it's learning at a sequence level.
Yeah, yeah. Okay, so and put it also here. The update equation is this one here.
But that's the normal thing, Vlad.
Right, I think it's the sum of the.
Yeah, which is the Frobenius norm.
Is it
It's like if you have the two norms squared, and that's the property of it that just sums up the squares. Then you collect everything into a matrix, then it just like, take differences of the entries of the matrix square and sum.
I see.
But whether you do
that's
that,
true.
it doesn't matter.
That's true.
Yeah. So that seems to be the normal thing, except that, well, people would use cross entropy or whatnot, but
Yeah.
okay. So this is just a normal thing.
Oh, sorry?
This is just the normal thing.
Yeah. This is just the loss, and yeah, basically the norm is squared.
Oh.
And here we get to the training dynamics with the results. So, want to explain?
Yeah, so here we're defining O of k as the kth column of the ground truth label. Like go to our so for each tree coming from the training distribution, at each reasoning step, what you do is you get the k minus 1th input and the k minus 1th output, and the main thing here is that this is from the ground truth. So it does not consider the output that the LLM is getting. It's from the ground truth, and you just get the output at the kth step using the transformer that we had done. Using the transformer, and you just take the last column of it, and you just put your overtrain like output as these from steps like 1 to k, like these steps 1 to k, and I think I tried put the loss, and you just take the loss over here. So this is like, since you are not allowing, or you are using the ground truth label with concatenation with this, there was the paper which talked about the clever Hans cheating thing. So this is why this happens, where they argue that when you are giving this ground truth label, you are somehow inducing a mechanism such that the output relies on the ground truth rather than its own token. So that was the main reasoning behind if you are going in the forward path, when you want to predict the next token, you are giving the actual ground truth previous token instead of the output that the model gave you. So it tries to induce some cheating, and once this cheating is learned, where it's just like a basic simple look ahead, because if you have the ground truth label over here, you just need to actually look at the edge list and get the next node. So if you have the ground truth label, it kind of learns this cheating, and that Pitfalls paper argues that once the cheating is learned, to go from the start node to the next node is a difficult problem. So this is what this paper doesn't talk about this issue. This was Chaba had asked us to look at this paper as well. So yeah, there were that paper uses some teacherless methods as well, which we won't get into. But yeah, so this is like just a implication of this teacher forcing issue that is there.
Wait, but these guys are also doing the teacher forcing.
Yes.
But the data is different. That's the main thing, right? Like in this case, they create data such that the difficulty of learning is just gone, because very simple transformations of the input from the point of view of the transformer needs to be learned. So no difficult computation. Like the next token prediction became a really trivial, like lookup and copy operation.
Yes.
Which, after all the simplification they do, I'm sure they show that the transformers can learn.
Right.
Yeah. I think so. Maybe the main lesson from this is that an originally possibly hard to learn problem becomes easy to learn if you change the data that's associated with it.
Yeah.
Okay.
So yeah, after providing all the reasoning, like you said, removing all the difficulties, all the hardness that was to the problem, the model can just basically learn, just follow the data set as much as you want, as it wants. It doesn't need to develop a new strategy or something like that. Anything else basically follows the data set and the problem is solved. And here we have a theorem that with these many time steps, training steps, we can learn the problem. We can learn how to solve the problem. So one of the main thing here it's the eta, which is like the bound for the training error. And the other things here, m is the depth of the tree that we're using to train the model. S is the number of nodes, and yeah, we have the abound. They also prove abound for the test loss, which basically depends of the size of the previous tree, of the training data, and the size and depth of the test one. So they have a nice relationship here of how much it can generalize basically on the ratio of the complexity of the training problem and the test problem.
Okay, I'm confused about that, but
Okay.
I have a hard time. Okay, there is an eta there. I see.
Yeah.
So that suggests if I make eta 100 billion, then I win. Like the larger the eta, the smaller the sample complexity. There must be some price for using it. Oh, eta maximum value is 1, then I should be just using 1. I see. Like there is no point of using any. Okay, that sort of makes sense because it's kind of a smooth problem, so you want to use the largest step size. That's a load. Uh-huh.
I guess I also had a question. So, so here, like the data is given in the form of these edges, right? Pairs of nodes, and we were saying that's what makes the problem easy because you just have to look up for each pair. And, but in the parity problem, which is hard, the data was given in a different form, and there it was not pairs of nodes. Was it just given? Was it the problem that it was given in the form of zeros and ones, and you have to implicitly transform that into pairs of nodes using a certain rule?
No, the star graph thing, like the parity, it was just to show like going to the next node from the vertex is as difficult as the parity. So we constructed it in such a way that it reflects the parity problem.
Yeah, that's fine. But I mean, it's the same problem here, right? You have a graph, you have a bunch of edges from the graph. They're given.
No,
you
the
the
first thing to predict, Roshan, after the prompt is presented, is very different here and there.
Oh, so you're not allowed to use chain of thought there. You're not allowed to go backwards from the thing and then reverse.
Yep.
Okay, I see. That makes sense.
And that's what makes that hard.
Right, right. So here the entire easiness is just coming from chain of thought because the backward path is easy and reversing is easy and chain of thought can do all of this. Okay.
Yeah.
What is M tilde?
Oh, it's the size of, it's the depth of the tree.
But okay, M, okay. And what is capital N?
Capital N. Oh,
I haven't seen capital N before.
Yeah, I forgot what's capital N.
And what's the data?
Oh, there is inside the log there's a
What's
capital N, but what is the embedding dimension?
The embedding dimension is D1.
But it's not in the bound. But I suppose it has to be set to be something.
Not necessarily, they just use D1, and in the examples they set D1 as 1.
What?
I guess there was this condition on the existence of B. I think does that imply some bound on the embedding dimension?
B.
The B matrix had to have this property that A transpose BA goes to the identity matrix.
Oh, that's it.
Yeah.
I see.
Um,
I see. So it's like that's where the vocabulary is kind of hidden.
Right. Yeah. So we are just assuming that there exists this key value matrix, but that cannot exist if the embedding dimension is small.
Right.
I think N is the number of distinct nodes, right?
yeah, N is the number of distinct nodes.
And what is S then?
Right.
S is the total number of nodes in the tree. I think they make a difference here of the ones that are used in the problem on the solution, the ones that it's like the totality of the tree.
Okay. So the tree doesn't have to include all of the nodes.
Yeah.
It's the size. Okay.
Yeah.
What do you mean by distinct nodes? Like in a tree, like isn't each node like distinct?
So you have like a full set and you are just using some nodes from it. So the total number of, like, your entire set is S, you are using n of them.
Oh, so S is the size of the alphabet and
Alpha.
Yeah, it's the size of the alphabet, and the other thing is the size of the
number
the
of nodes in the tree.
Yeah.
number of nodes actually used. There could be lots of unused nodes. Yeah.
Right. So how do we interpret this result on the test error? Can you explain that?
So, okay. So first we have this bound here for the train data, which is epsilon. The train data is at maximum, at most epsilon. And here we are saying that we have at most 4 times, and here, let me go item by item. So 4 times the epsilon, and we have here m, it's the depth of the tree, and m tilde, it's the depth of the test, the test tree, the test data, the tree in the test set. So basically, if this, for this here to be bigger than 1, we are going to have like a harder test problem than a trained problem. So this is basically what it says. So if we have like an easier, we train, for example, depth 5, and we are testing depth 10, we are going to have like double the epsilon at least, at most, in this, for this term here. So, and for this one here, it's something similar to, so n, it's the number of distinct nodes, and these on the upper part of the fraction, it's for the test problem, and on the bottom here, it's for the training problem. So we are using, you can think this like the first one. If the problem we are testing on it's harder, it's going to be bigger. If the problem we are testing on it's easier than the training problem, it's going to be smaller. But we are also having a minimum here of 1. So this term here, it can't, the number of distinct nodes doesn't matter to like reduce this bound, to like lower this bound. It can just increase the value of the bound.
And somehow it's not the same for m tilde, the other term. Like if m tilde I set it to 1,
Yeah.
then like I get a boost of performance of 1 over m.
So I don't think I understand the question.
You said m tilde as 1,
Yeah.
so we like n tilde upon n plus m minus 2.
And compared to the epsilon I have epsilon over m, which means it's getting better.
Yeah, it could get better if you try on an easier problem.
Yeah.
If you test it on an easier problem. So yeah, let's use example values. So for example, if you trained in a, I don't know, depth 10 tree, we are going to have, let me use a nicer number, a depth 8 tree, and now we are training, or we are testing on a depth 2 tree. So this term here, this fraction here, would be 1/4, because it would be 2 over 8. And this here, it would depend on the number of nodes. So, but for the, like for, if you are going to test on a harder problem, this here, it's going to be lower than 1. So this maximum here is going to be 1 for sure. So the bound here will be reduced to 4 times 1 times 1/4 epsilon. So in this case here, we would have like just epsilon at the end. Yeah. So the bound would be reduced. The test bound would be lowered to the same bound as the training bound.
By the way, the training bound, the way you wrote it, it's an expectation over these random examples. Does the distribution of the examples matter?
They say they uniformly sample it.
So what does that mean? You can do that in many ways.
Okay, so yeah, what they say is like, for example, for one of the tests, they set the M, and they put random numbers to the values on the nodes, and that's what they use to uniformly sample the problem. And
You also
solve
have
the
to select the
problem.
edges and what's connected with what.
But I guess it's a uniform distribution on all trees of depth M, right?
Yeah.
And the way you would get that is by taking select one node, randomly select its parent, and then just keep repeating, right?
Yeah.
I mean, okay.
Yeah.
But the structure of the edges might be different.
It doesn't matter.
No, but
as
they
long as you
train.
select-
That's the thing. They
yeah.
train on perfect binary trees.
Uh-huh.
So the
It's
trees.
always perfect binary trees.
Yeah. The training here it's on perfect binary trees.
So does it matter? You think it matters whether it's perfect binary trees or?
I don't think so. I think this result, like they also say that on the paper, that it's possible to extend this result. I don't think we need to adjust perfect
Okay.
binary trees. Yeah, but like if
So,
you have
but
like
okay, so the real question was that it's an expectation, the training loss. So, how does it differ from the test loss? I said that like the training loss is usually you have some training data and you would define a training loss against the training data. This more looks like the test loss to me.
Yeah, I had a question about this too. I thought the Frobenius norm was hiding the fact that we actually have capital T samples from the train distribution.
Nah.
And
Okay.
and
I
like,
see.
isn't theta here also random dependent on the train? Like, I don't get, yeah. Because then how do we claim that the train loss is less than epsilon and there's no expectation or high
There's a
probability?
train
of it?
loss and a test loss, and are they the same, different?
Or and like also, why is there a Frobenius norm if it was not on the like data set of size t, right?
Oh, it's because for every sequence you have like a bunch of vectors, you stack them in a matrix, and then you just take Frobenius norm. There's just sum of two norms.
Yeah,
Right.
but here you only get
On
one
the
graph.
vectors, and so you just don't want to write everything out. Like you happen to choose this matrix form for O, but you really just want to use two norms squared. You're forced to say it's a Frobenius norm. Because like what's your data? It's like there's this XY and then like you have, so it's a matrix. That's your data.
No, like one graph is just one sequence.
Yeah, but like the sequence had the X and a Y, and like you remember the encoding?
Oh, sure.
So
Okay,
every
you think
sequence
of it
is
like
vector. And it would be an embedding vector anyways.
So if you
I
wrote
think.
everything in one row, it would be 2 norm squared, but
Yes.
because you wrote it in 2 rows, it
That.
becomes
Okay,
Frobenius
well,
norm
okay.
squared.
If that's what they mean, I
Yeah.
didn't think
So,
that's
that-
what
that's-
they would take
that's
this as the whole output of the big O is basically this. So they just
Okay.
subtracting the both matrix and
Oh.
taking the square of each term and summing everything up.
Oh. I thought this, okay, that's not what I understood.
Yeah.
Then I am confused what this L train of theta less than epsilon means.
They're just trying to prove convergence over here, that using such path, like at least for the backward, yeah, this for the backward thing, if you use the B such that A transpose BA is equal to
I guess
I.
like that theta
Mhm.
will differ if your data set, like you have a data set of size t, and if you get a different data set, you get a different theta.
Mhm.
So that L train is like a random variable, and theta is a function of the data set you sampled. So I don't.
I don't think T is the length of the path, but
T is the number of graphs you have
no.
to train from, right? Capital T.
Yeah, T is drawn from your training set, and the whole thing is the function of theta.
Yeah.
So that's a loss of a particular parameter theta. And the loss is an expectation over data from the training set.
Wait, I
Is
think
it?
T's-
Yeah.
I don't see that.
Oh, I see. It's like it's an empirical distribution or something.
I don't get it.
Like the whole thing, like the theta is the thing that you're computing the loss for,
Yeah.
and the loss itself is an expectation, and the expectation is over t drawn from the training set.
Right, but T is a single data point, and your training set would have capital T taus.
No, okay, so that's how many steps you run the algorithm for.
I think that's it.
Like little t is like the algorithm step, right?
Yeah.
This here is
Oh.
the training steps. It's the T here. It's the training steps.
Oh.
So it's full gradient. It's not gradient, not stochastic
wait,
gradient.
oh.
Nothing.
Oh, T
By
is
the
not-
way, so
Oh.
this last result that says
Wow.
that if you push the training error to be epsilon, then the test error is going to be at most this much times epsilon. This is like a generalization bound, right?
Yeah, that is the generalization bound. Yeah.
Okay. How do they prove that?
Okay, so the proof is quite big. They have 60 pages of proof. Yeah, it's
No, not for the generalization bound, but
yeah, like yeah, I couldn't
It's not-
understand fully the proof. It's too much
Yeah.
stuff. The math was too complicated, but yeah, they have to have those structures on the weights for them to be able to do that. Yeah.
I guess okay. I would have a proof strategy, but I guess maybe there are the ideal weights, and you prove that the true weights converge to a vicinity of the ideal weights, and then based on that, you can get this bound or something like that. Yeah, but at least I would expect that the training set is drawn randomly from distribution over all the binary trees, I suppose, like the elements in a training set. Therefore, the training set is random. Therefore, the parameter that you get is random because you are training based on the random data.
Yeah.
And then the test error, is it going to be, like you plugged in the random parameter into the test loss. That should be a random quantity. So I expect this was with high probability or in expectation or something like that. Did I say something about this?
No, they do not say something about probability of convergence. They just say that it will converge.
Okay, I check. All right.
Maybe theta is expected. Or no?
No.
No?
That would, yeah, that wouldn't be too easy to do.
What is
I don't
the
know.
data set size?
Yeah, it's something. But like what I noticed is that like usually you see the dimensionality of like even linear regression.
Mm-hmm.
Okay, so
I guess I'm wondering. Okay, so if you are in the realizable setting, you don't have any noise, and the only noise that you have is from the covariates, and you guarantee that the train loss is epsilon. What can you guarantee in linear regression about the test loss?
What do you mean by train loss?
Well, the training loss would be over we don't even know how many training data points do we have.
Because then it's like.
Oh,
the
that's
same.
what you were pointing out.
Yeah.
So if we don't even know that, then how would we know that we didn't have just a single training data point? And then, okay, you drove the training error to be small, but it's not. That will make the test error small.
So is the training set the size of the number of binary trees?
So
Right.
what they say here, it's like they for the proof to work, they have an assumption that they're training over all perfect binary trees. So
Right.
this
Oh, the training and the test loss are the same. But then why is there a difference? Oh, it's because they want to talk about that.
Different-
Okay,
yeah,
either
you
bigger
can change the
trees
depth.
or
They
smaller
train on a
trees.
fixed
I
depth.
see.
So the
I see what's
distribution
going on.
changes.
It's not the usual train testing. I just say that, oh, like if I have complete data, then I can prove this thing works. And then, out of curiosity, I can ask whether it works if the size of my trees is different than the size of trees
yeah
I
on the
use
training.
for training.
Yeah.
Okay. Okay, now I understand.
Okay. They use the expectation here, so now I get it.
That's
they are
fine.
using all the
Now I
trees to
understand.
train, all of
Yeah.
them, so it makes sense. And also, there's just one more detail. They do experiments on this paper, and of course, it works. And yeah, it's everything under the bounds and the convergence. They also test that it works, and yeah.
And does it match the M and M tilde? Does it like the ratio of?
Yeah, it was not like exactly to the bound, but it was lower than the bound.
But that means the bound is too big, I guess.
Yeah.
But isn't that what you'd expect? It's like, what you get in
No,
your
yeah,
tutorials.
I meant like the behavior. If you're expecting it to be M tilde or M, then
Yeah.
you would expect like if you double the size of the depth of the tree, then the error should double and stuff like
Mhm.
that, right?
Yeah.
Maybe that's asking too much.
I guess in the loss you are averaging over the lengths or something. Like there is a length. No, not averaging. It's like it's dependent on the length. So the loss gets bigger if you have longer sequences. That is the depths.
Right.
That's the M dependence. So I totally understand this M tilde over M.
Right.
That just normalizes the loss in a proper way.
Yeah. Okay.
The other one is okay. That's complicated, but
Yeah. So
Okay.
capital N and L tilde were the number of nodes used in the training versus
Yeah,
the test.
yes.
Okay. So that's more interesting, right? Because the number of different binary trees is kind of has an interesting dependence on the number of different nodes that can be there.
Yeah.
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 Okay.
All right.
Was MD.
I need to go.
Okay. Yeah. Yes.
It's time.
Yes.
Okay.
Yeah. Okay. See you guys. Thank you.
Thank you all.